This is an overview of the National Science Olympiad Reach for the Stars B event for 2016. The content focus this year is stellar evolution, star formation, and supernova remnants. The competition will be held at the University of Wisconsin Stout in Menominee, Wisconsin on May 20th and 21st. My name is Donna Young. I'm an educator for the NASA Astrophysics Division, and the NASA Astrophysics Division is the sponsor for the Reach for the Stars event as well as the astronomy event. This webinar will be posted on the Chandra X-ray Observatory website under Science Olympiad Educational Materials, and later on towards the end of the presentation, I will talk about the resources and other URLs where materials will be posted and made available for you to use to study the competition. The PowerPoint presentation accompanying this webinar will be posted on the AAVSO website, and I will give you that URL at the end of the presentation. So this year, Reach for the Stars Division B, this is the first year of the 2-year rotation. It has been planetary science for the past 2 years. So now we have 2 years of Reach for the Stars. So the event description is very similar to what it was in 2013. Students will demonstrate knowledge and understanding of the properties and the evolution of stars, specifically oriented towards the star formation regions, the big star formation complexes, and supernova remnants. And it's very important to be knowledgeable about the multi-wavelength aspect of studying stellar evolution and star-forming regions and supernova remnants, ranging all the way from radio through gamma ray. The event parameters are that each team may bring 2 pieces of 8.5 by 11 inch pieces of paper covered front and back with information in any form from any source. Coaches should contact their state director if they should be holding the state competition in a planetarium. Then teams are required to bring flipboards and little red flashlights so that they can see to answer the questions during the event. The event is divided into 2 parts. The first part is star and constellation and identification, and where the deep sky objects are located within those constellations. The second part deals with stellar evolution and the spectral classification of stars, observing them in multi-wavelength portions of the spectrum, the relationship between stellar temperatures and radii and luminosities, and the magnitude and absolute magnitude and luminosity scales, and the distance modulus and the inverse square law. And we will be going through those in a little bit more detail towards the end of this presentation, but bear in mind this is just a very general overview and does not go into very great detail. Part 1 for the constellation star and deep sky object identification. The constellations that you need to be knowledgeable about for this year are underlined. The major stars within those constellations are in bold type, and the deep sky objects are italicized. If you look at Part 2I, which is on stellar evolution, and we go back to those deep sky objects and we divide them into categories of objects, there are 10 star formation regions, 4 specific supernova remnants. There are 3 unique stellar evolutionary stages. One is a planetary nebula with a white dwarf, one is a stellar mass black hole, and another one is a very young open cluster of hot young stars. There are also 2 galactic deep sky objects. One is the Large Magellanic Cloud, which is a neighboring galaxy, and the other object is Sagittarius A Astric, which is the massive black hole at the center of the Milky Way galaxy. And don't forget that those constellation stars are also in various stages of stellar evolution, and you might keep that in mind as you're working on the identification part of this event. So briefly, stellar evolution, as we go a bit further along with that particular idea, keeping it in your head all the time, we are going to be looking at stars that are just starting their evolutionary history as protostars, and then we're going to not so much pay too much attention to what happens to them while they are on the while they are normal stars when hydrogen is fusing into helium, and then we're going to be looking at the masses as they transcend from the protostar through the giant and supergiant branches where they actually become planetary nebulae, white dwarfs, and supernova remnants, both type 1 and type 2. We'll be talking about that. And I'm going to be using HR diagram technology to describe some of those deep sky stars that you're responsible for. So I will give a little bit more detail about the HR diagram, Hirschsprung-Russell diagram, at the end of the talk. But just for you, those of you who are doing stellar evolution for the first time, because we hasn't been done for the past 2 years, basically the main sequence, this is just a plot of spectral class or temperature versus absolute magnitude and or luminosity. And when you plot those two characteristics, physical characteristics of stars, they end up in very specific regions on the HR diagram. It's a scattergram plot. The main sequence is where stars reside when hydrogen is fusing to helium in their core, and they are a normal star. And the giant branch and the supergiant branch are where they exist when they have transitioned from the main sequence. They're no longer fusing hydrogen in their core. They're fusing other materials in their core, going through their sequences till they reach their ultimate collapse into remnants or planetary nebulae. So there is a giant branch and a supergiant branch, and then there is the white dwarf branch down towards the lower left-hand corner of the HR diagram. So I'm going to be talking about on the main sequence, on the giant branch, on the supergiant branch. We're going to be talking about luminosity. Now, luminosity is also split into different categories of luminosity. So, and they start with the supergiant. In the supergiant region, you have luminous supergiants, and those are 1. And in this particular HR diagram that I'm showing here with luminosity classes, it has it split into A and B. But the most luminous class is 1. The a little bit less luminous, but still supergiants, are the class 2. Class 3 are the red giants on the red giant branch. Class 4 are subgiants. They've transitioned off the main sequence on their way to the giant branch. And main sequence stars are class 5, the V. So bear that in mind as we go through and talk about these stars that you need to identify on this year's competition. In the constellation of Aquila, there is Altair, and Altair is an A spectral class star. It is on a transitioning from the main sequence to the subgiant branch, so it has started evolving from the main sequence. And in that region, the W49 region, in that particular constellation, when you start searching that, you will see that there are 2 objects that are the only 2 really important, well-observed objects in that particular area. There is W49A, which is a stellar nursery, and there is W49b, the other end of the evolutionary spectrum, which is a type 2 supernova remnant that is thought to have a black hole in its center, the collapse of a very massive star. In Aquarius, the constellation Aquarius, there is a deep sky object this year that is the Helix Nebula. And the Helix Nebula is a planetary nebula with a white dwarf. So this was sort of a sun-sized star, main sequence star. It ran out of hydrogen to fuse in its core and went through a red giant stage and then did a sort of, astronomically speaking, mild collapse. And when the core collapsed, it rebounded a little bit, connected with those infalling layers of atmospheric material surrounding the core of the star. And those got sloughed off into the interstellar medium and left a white dwarf behind. And the planetary nebula itself just spreads out through the interstellar medium, getting more and more tenuous over time, and eventually disappears and leaves just the white dwarf behind. So planetary nebulas are quite young, about 50,000 years, and then they become invisible optically.